Welcome to ES 310 Lesson 7. Today we'll be continuing the work we started in Lesson 6, looking at the force equals mass times acceleration equation and how that helps us find the kinetics related to the kinematics of these types of dynamic problems. Today we'll be extending that to the other two types of coordinate systems that we've studied, the N-T normal tangential coordinates and the polar or cylindrical coordinates. For more information about this topic, see Hibbeler's Dynamics Text, Chapter 13, Sections 5 and 6, and to review the N-T and cylindrical coordinates, take a look at Lesson 4. Just as a quick review of our coordinate systems. The rectangular coordinate systems are what we are most familiar with and what we used in the last lesson to implement the force equals mass times acceleration equation. The tangential normal coordinates are usually used when something is known about the path, which tends to be a curve. So you may know the radius or you may know the expression for that path. And then we would use the tangential normal coordinates to find the velocities and the accelerations. In this case, there's one component of the velocity, and there are two components of the acceleration, one that is tangential or along the curve, and one that is normal or towards the center of the curve, which is sometimes called the centripetal acceleration. In the polar or cylindrical coordinate system, we have a coordinate system that is fixed but rotates. And so there we typically know information about that rotation, whether it be the rotational speed or the rotational acceleration. In this case, both the velocity and the acceleration have two coordinates, which can be solved for so long as you can solve for r, r dot, r double dot, theta, theta dot, and theta double dot. So, in Lesson 5, we looked at Newton's second law in rectangular coordinates. The procedure we used was to identify the reference frame, place our x, y, z axes, and make sure that reference frame is not accelerating, though it could be at any angle. Then we drew our free body diagrams showing all our external forces, and we identified the expected direction of our acceleration, which could be a guess if we had no idea. We applied Newton's second law, which is the sum of the forces in any given direction is equal to mass times the acceleration in that direction. And that gave us up to three equations if we were working in 3 dimensions. And in some cases we needed to use our kinematic equations to relate those accelerations to velocities, distances, or time. We're going to follow a similar method in our N-T and cylindrical coordinates. So we're going to establish an inertial reference frame. In N-T, we're going to establish a normal tangential reference frame. We're going to draw our free body diagram showing all of our forces in the N-T directions and breaking up any force that isn't in the N-T direction into components along the N or the T. We're going to identify the expected directions of our accelerations. We have two components in this case, so AN will always point inwards towards the center of curvature for the path, and AT will always point in the path direction. Then we apply Newton's second law, and we use kinematics again. So Newton's second law in this case is going to be in the normal tangential direction. So we've got the sum of forces in the tangential direction is equal to mass times the acceleration in the tangential direction. And if you remember from Lesson 4, the acceleration in the tangential direction is simply v dot, or the derivative of the velocity. Similar equation for the normal direction. Now the acceleration in the normal direction is v squared over rho. So we will use that expression. Rho is the radius of curvature. Sometimes that's given to us, and sometimes if we're given the path as a y as a function of x, then we will have to take derivatives in order to find rho. But we should be able to find rho. If we're dealing with the third direction, the B direction, which is perpendicular to T and N. So if something's moving along a path, the B direction would be coming out of the screen at us. The sum of the forces in that direction are always going to be equal to 0. So let's take an example of this. So this example is a 2D example with a changing row. We're given information about the path. In this case, we're given the equation for the path. And so that's what should give us the hint that we will be using N-T coordinates. So if we take a look at what's happening here, we have this car that's going over the hill, and we have an equation for that hill. When the car is at point A, x is going to equal 80, right? And we know that v, the speed, is equal to 9, and the speed is increasing at 3 meters per second squared. So we already know this is AT, right? Because our equation for AT is v dot. We need to determine both the resultant normal force and the resultant frictional force that all the wheels on the car exert on the road at this instant. And so the normal force is in the N direction, the frictional force will be in the T direction. Alright, so let's start with drawing our free body diagram. So I'm going to exaggerate this somewhat, but the car is at A, so it's got a slope. Here's our car. Alright. The normal direction is normal to the car. The frictional direction is, if the car is going down the hill, the friction between the wheel and the road is what's making it go down the hill. It's not sliding in this case. The friction is actually causing the car to move. So this is going to be FF, this is going to be N, and the car has some weight which goes straight down, mg. Alright, so now we need to draw our coordinate system. We've got our normal direction, which is towards the center of the curve, right? So our normal direction is in the direction of our normal force, pointing in, so that's n hat. And our tangential direction is along the curve, in the direction of motion, right? So we're going to say that the acceleration tangentially is going to be that direction as positive. The acceleration normally is going to be that direction as positive. Oh, those don't have hats on them, they're just vectors. There we go, they're vectors. Alright, so here's our free body diagram. N and FF are in the directions we need them to be. mg needs to be broken up into components. So if we break this up into components, we've got a component along the N, we've got a component along the T. We need to figure out what that theta is, right, in order to break that up into components. That theta is the same as this theta, right, just based on geometry. This theta, we have the tangent of that theta is equal to the change in the y direction, right, which is the opposite, over the change in x, or we could write this as the derivative of y with respect to x. At this particular point, x is equal to 80, and we'll find that in a second. So now we have our free body diagram. We can write our equations of motion. We're going to have to come back to them because we're not going to know everything in there, but we can start with that. So let's write the sum of our forces in the, we'll start with normal direction. So we've got negative n, right, it's pointing out, and the normal direction is pointing in. Negative n, and we've got part of the mg, which is going to be positive, it's pointing in. Mg, and it is the cosine part because it's adjacent to the angle, is equal to mass times the normal acceleration. And we've got the sum of forces in the tangential direction. So FF, which is positive, pointing downwards towards, in the same direction as T, plus we've got mg sine of theta, also positive, right, pointing in the direction of t, is equal to mass times the acceleration in t. And we already know the acceleration in t. So we need to find the acceleration in n, and then we should be, and we need to find theta. And then we should be able to use these two equations to solve for the normal force and the frictional force. So how do we find theta and how do we find an? Well, an is going to be v squared over rho, which is going to be 9 squared over this radius. So we're going to have to find rho and we're going to have to find theta. if we find both of those in the same process. So let's start with our expression. Let's start with the y direction. So y is equal to 20 times 1 minus x squared over 6,400. dy dx is equal to, the constant derivative is 0, so minus 20 is the constant, times 2x divided by 6,400, which can also be written as negative 2x over 320. And then the second derivative, d squared y dx squared, is equal to, take the derivative again, negative 2 over 320. So at 80, or, well, everywhere, negative 2 over 320 is equal to negative 0.00625. At 80, which is the point we're interested in, this is equal to negative 0.5. Alright, well, we found dy dx. dy dx at 80 is equal to the tangent of theta, so we can take the inverse tangent of 0.5, or negative 0.5, and we get, let me find that, 26 degrees. 26.6 degrees, in fact. Alright, from this, the first and second derivatives of y with respect to x, we can find rho. Right, because rho is equal to 1 plus the first derivative, which is negative 0.5 squared, to the 3/2, divided by the magnitude of the second derivative, 0.0625. Plug those numbers in, we get 223.6 meters. Alright, so now we have rho, so we can put it in up here, and we can find AN is equal, so this is going to be 9 squared over 223.6, which gives us 0.362. And we have theta, so now we can go back to these two key equations, plug some things in. So we have, in the first one, we have rearranged this. We're solving for n, right? We should have everything other than n. So n is going to equal m, let's plug things in. M is 800 times 9.81 times cosine of 26.6, and that then minus 800 times AN, which is 0.362. So N is equal to 6,727 newtons. That's one part of the equation. Alright, I need some more space here. We will use the second equation, so we'll solve for F of F, is going to be the mass times the tangential acceleration, so 800 times 3 minus 800 times 9.81 times the sine of 26.6, which gives us 1114 newtons. So, as a review, we started with the free body diagram. We drew our normal tangential directions. We wrote our force equations. We noticed from our force equations that we didn't have all the information we needed. So we went and we found AN and AT from the definitions of AN and AT relative to the various velocities. So that's from the kinematic equations. We needed to find theta and rho, which we got from the derivatives of the expression for the curve. And that gave us then our solution. Let's take another example where we move into 3D and we use that equation, the B direction, the perpendicular direction. So we've got an airplane, and as you know, when an airplane turns, it dips its wing one direction. right? So it dips its wing into the turn, and that's what allows it to make its turn. So this airplane is traveling at a constant speed of 50 meters per second. So v is 50, and it's constant, so v dot is 0. And it's making a horizontal turn. Okay, so gravity is going down, right, in this turn. And to do that, it's banked at an angle of 15 degrees. When it happens to be at 15 degrees, the pilot experiences only a normal force on the seat. And we need to figure out what this radius is for this to happen. And then we need to figure out what is that normal force if the pilot has a mass of 70. So first of all, let's talk about directions. So this is horizontal. This plane, the tangential direction would be that way, right? The normal direction is towards the center of the circle. And then this up and down direction right here is our B direction. Okay, now if you imagine somebody sitting in this plane, right, and we draw a free body diagram of him, he is going to be tilted at an angle of theta. So if we draw him, here's our guy, right? There's our guy. He's sitting on a seat in the plane. His weight still goes straight down. That doesn't look like straight down. Let me try that again. His weight still goes straight down, mg, right? And we've got a normal force pushing up that way. And in our case, if we now redrew this, right, so we're now zoomed in and we've changed our orientation so that we're looking down this tangential direction. So B is straight up in the air. N is horizontal, right, because N is horizontally towards the center. So that's our coordinate system, B and N. Here are our components. mg is directly along B. The normal force is not. So the normal force is the one we need to find the components of. Well, we're told that the plane is banked at 15 degrees. So this angle right in here is 15 degrees, because that's the tilt of the plane, which tilts the seat, which tilts the normal force. Alright, so theta is 15 degrees. We can now write the forces, right? So we've got the normal forces in the n direction. There's the part of n, and that's it. None of the mg is in the n direction. So we've got n, and the part that's in the n direction is the opposite part, so sine theta is equal to mass times acceleration in the n direction. And the sum of forces in the b direction is going to give us, let's see, we've got mg, which is in the negative b direction, and we've got the n part, the adjacent part of the n, which is the cosine part, and that is going to equal 0 because that was the equation. The sum of the forces in the b have to equal 0. Okay, and since the problem says he only experiences the n, we don't have to have a friction between him and the seat. So those are our two equations. What do we know here? We know m and g, and we know theta. So the bottom equation allows us to find n. N is going to equal mg divided by cosine of theta. We plug in all our known variables there. We end up with 710. Then we take n back up into this equation. So n times sine of 15 is equal to mass times an. We can solve for an as being 2.63 meters per second squared. Alright, now what were we trying to find? The radius of curvature, right? Rho? Well, we remember from the equation an is v squared over rho. V squared is given to us, and its units is meters per second, so we don't have to convert it. So 50 squared divided by rho needs to equal 2.63. And we can solve for rho then to be 951 meters. So as the plane is turning, its radius of curvature is almost a kilometer. So in this problem, just to review, we drew our free body diagram, we drew our coordinate system. In this case it was NB, we weren't interested in anything in the tangential direction. We wrote our equations of motion, or our Newton's second law equations, and we were able then to solve for our acceleration, and then we used our definitions from kinematics in order to find information about the radius. The process that we're going to use for the cylindrical coordinates is parallel to the processes we've used for the other two. All right, so we're going to start by establishing our inertial coordinate system. In this case, our inertial coordinate system is going to have an r, a theta, and possibly a z. So r goes from our origin out to our point of interest. That's its direction. Theta direction is in the direction of that changing theta, which is usually information that's given to us in the problem. That's how we know to use the cylindrical coordinate system. And z would be coming out of the slide at us in this diagram. We draw our free body diagram, break up all our forces so that they're either in the r, the theta, or the z direction. We identify the direction of our expected accelerations, or we take a guess if we don't know. And we apply our Newton's second law. So our Newton's second law for this situation, same form as before, sum of forces equal to mass times acceleration in that direction. We're using our kinematic definitions for AR, A theta, and AZ. So once again, remember, if we can find these three things so long as we know R dot, R double dot, theta double dot, and in this case Z double dot. And then we use any kinematics to write additional equations which we might need to relate things to position or time or velocities. So let's take a look at how this works. We've got an amusement park ride. You see a lot of amusement park rides when we're talking about polar equations. So we've got an amusement park ride. This guy is sitting in this cart, and it's supported by small wheels. Initially, the cart is traveling in this circular path, and r is 16 feet. And we're given the expression for its speed. All right, and so then r starts to change, right? So this rope, this cable in here, starts getting pulled in. So he's spinning and getting closer and closer to the center, basically. And we need to figure out what the tension in that rope is at the point where r has now changed to 4 feet. So it starts at 16 feet. When it gets to 4 feet, what's the tension in the rope? And we're told that the cart and the passengers have a total weight of 400 pounds. And we can neglect friction. So those wheels that it's supported on are frictionless wheels. So let's see how we would go about setting this up. We need a coordinate system. So in our case, we've got, here's our origin, here's our r. So r is going to be pointing outwards. And theta, so that's r hat, and theta is going to be pointing in the direction that theta is changing, so that is theta hat. And if this was in 3D, we'd have a vector coming straight out of the board at us, but we don't need to worry about the z direction. So nothing's happening in the z direction. Okay, so we've got r and theta directions. Let's draw our free body diagram. We have this guy in the cart, and really all that's happening is we have a tension acting towards the center. And no other forces are acting on this because the gravity is acting out of plane, right? It's going into the board. Okay, so sum of forces in the r direction is going to equal negative tension, right? It's acting inwards and r always points out, is equal to mass times AR. And the sum of forces in the theta direction is equal to none, 0, is equal to mass times acceleration in the theta direction. Now think back and remember what the expressions for AR and A theta were, and we get this is mass times r double dot minus r theta dot squared, and mass times r theta double dot plus 2r dot theta dot. Okay, now we need to use this hint that's in the orange box here. This hint is coming from differential equations, which I'm guessing none of you have had. But basically, you see this is equal to 0, right? So the mass goes away, so that means the stuff in the brackets here has to equal 0. It tells us that if that is the case, then we have an expression that then this simplifies into this first derivative with respect to time of r squared theta dot also being equal to 0. So this line means that we can say that r squared theta dot is equal to a constant. And that's coming from the hint from differential equations, but we're going to use that in a second. All right, so to find this AR and r squared theta dot and everything else, we need to know what all of these various r's are, okay? So let's start with what we know. We have an initial conditions, right? So initial conditions, r at 0 is equal to 16, and theta at 0, theta at 0 is equal to 0.2. So those are our initial conditions. We're also told that r dot is negative 0.5, and it's a constant, so r double dot is equal to 0. And we know our mass, we'll write that here, our mass is given as a weight, so our mass is 400 divided by 32.2. Okay, so if we know r dot, we need to find r. So how do we get to r from r dot? We integrate. So we're going to say if r dot is equal to dr dt, then dr integral is going to equal the integral of r dot dt. This is going to be from 0, from the initial, which is 16, to the point we're interested in, which is r. This is going to be from the initial, which is t equal to 0, to the time we're interested in, which is t. So this is going to be r minus 16 is equal to r dot, which was negative 0.5, so negative 0.05 times t. All right, so our expression for r then is r is equal to negative 0.5 t plus 16. So at what point we were interested in? 4, right? R equal to 4, t equals 24. So it took 24 seconds for the r to go from 16 to 4. So we have the r information now. Now we need the theta information. Well, here we have the fact that theta dot is equal to some constant over r squared. Can we figure out what that constant is? Well, this is always going to be true, so it's also true at the initial condition, right? At the initial condition, theta dot is equal to 0.2. And we have r is equal to 16, so we can solve for the constant, right? So 0.2, let's go back up to this form of it, right? R was 16 squared times 0.2 is equal to the constant. So the constant is equal to 51.2. So we then have this expression for theta dot, which is 51.2 divided by r squared. So at this point where r is 4, so theta dot at this time of 24 seconds, which we found down here where r is 4, is going to equal 3.2, which is 51.2 divided by 4 squared. So we now have r dot, r double dot, r, theta dot, and we don't need theta double dot. So it doesn't matter what it is, right? Because we're going back up to this equation. We have r double dot, r, and theta dot, all at this point where r is 4. So I'm going to call this equation 1. We'll come down here and finish working with equation 1. The negative tension is going to equal the mass, 400 divided by 32.2, times r double dot, 0, minus r, 4, times theta dot squared. Theta dot is 3.2 squared. So the tension is equal to, so the negative signs will become positives, right? And the tension will be equal to 509 pounds. And that then is our answer. So, methods again. We drew our coordinate system. We drew our free body diagram. We wrote our equations of motion. We used information that we knew about the kinematics to find all of the variables we needed in order to fill in the equations of motion. We solved the equation of motion for our unknown. In this case, we used this hint, which had to be given to you. There's no way that I would expect you to know this because you haven't taken differential equations.